Assalamualaikum warahmatullahi wabarakatuh and very good morning. So we are going to continue for chapter 4, which is on the part 3. Okay, let's look at this slide. So we are going to refer to the Fourier transform by referring to the appendix. So if you refer to the Fourier transform appendix PDF, so we are going to look at the rectangular t over t. T is the period of the rectangular. So if we have the rectangular, we have the period, the rectangular t over t. So we can actually write out the value is t sin omega t over 2. So if you have the amplitude, rectangular have the amplitude a, so you have a t sin omega t over 2. Okay, so we are just going to look directly to the example 1. Okay, so this is by referring directly with the Fourier transform table. So in comparison to what you did in the previous in last week class, so you actually derive the equation from the given Fourier transform equation. So now we are going to directly use the Fourier transform table to actually get the Fourier transform for this signal. So let's see that you have the rectangular signal here with the value of given for a amplitude a from minus t over 2 tau over 2 to tau over 2. So you have this value or this signal, then let's go and find what is the Fourier transform for this signal. So by referring to the table, you have a rectangular t over t here, so which is you write out this equation. So by referring to the Fourier transform pair table given in the appendix, so you can see that you have the time function here and also the Fourier transform given for the each time function. So let's say that we are going to look at this rectangular t over t. So you can see that the Fourier transform is given by t sin omega t over 2. So just now, like I said, if you have the amplitude a, so a rectangular t over t, so you have here is a t sin omega t over 2. Okay. Okay, so after referring to the appendix of the Fourier transform pair, then we can see that we have actually a t sin omega t over 2. So we have the value a is given by the amplitude and t is actually the period of the signal itself. So from here is that you can determine what is the period of this signal. So this signal is given from the period minus tau over 2 to tau over 2, means that you have the period t equal to 1. Okay, so therefore substitute 1 into this term, so you have a times 1 sin omega, this is t, so substitute t equal to 1 over 2, so you have actually the final answer is a sin omega over 2. Okay, so if we refer to the example 1 that you have did in the previous examples, is that you can see that you actually will get the same final answer. Okay, so means that you can easily use the Fourier transform table to actually answer the question for Fourier transform, given that if they do not say derive the equation using the Fourier transform equation. So let's look at another example. Okay, when we have a different value of t, so we have this is t over equal to 1, t equal to 2, t equal to 1 over 2, then t equal to 4. So the difference is that the period here, okay, the period for t equal to 1 is from minus t over 2 to t over 2. So therefore this is what you did in the last slide. So this one is same as example 1. So let's say that we look at the second example. So we have the period from minus tau to tau, so means that the period itself is equal to 2. Okay, so substitute the value, so you have a rectangular, refer to this equation, a rectangular t over t equal to 2, so t over 2, so you have a t equal to 2 here, sin omega 2 over 2. So you have the final equation for this signal is 2a sin omega. Okay, so let's look at the next example. So when we have minus tau over 2, the period is from minus tau over 2 to tau over 4. Sorry, tau over 4 to tau over 4. Amplitude is A. So from here is that you have the t value is 1 over 2. So substitute the value of t, you will get t over 1 over 2, and final answer you will get a over 2 sin omega over 4. So this is the same, similar to example 1 that you did in the previous slides. Okay, so you can just compare the one that you derive it manually from the equation given, and the one that you refer directly to the table, you will get the same answer. So meaning that if in the midterm exam or in final exam they do not use the equation or derive it, then you can directly use the Fourier transform table pair. And lastly is that we are given the period from minus 2 tau to 2 tau. So t, you will have t equal to 4. So because you have the left side is you have 2 tau, and from the opposite side is we have 2 tau. So you get total 4. So when you rewrite again this equation here, okay, you write this, then you will get a rectangular t over 4, t equal to 4 here. So you get a 4 sin omega 4 over 2, so you get sin 2 omega. So you will get this final answer. Okay, now we are going to look at the properties of Fourier transform. So similar to what you learned in chapter 1 on the properties of continuous time signal and discrete time signal, you learn about the time property. So you have time scaling, time shifting, then linearity, and so on. So we are going to look at the idea of implementing the property of Fourier transform in terms of scaling property, shifting property, and linearity into this Fourier transform. So let's look at the example that you have did in example 0. Okay, so we are going to look at the scaling property first. Okay, so you have the period from minus t over 4 to t over 4 with the amplitude a equal to 1. So I write it here. Okay, so you have a capital is the amplitude of the waveform. So a here is 1. Small a is actually the scaling size. So remember, last time when you learned in chapter 1 is that when you have the scaling factor, so 2 times scaling factor or 3 times scaling factor means that the signal is being compressed. Means that when you have a tape recorder example, so if you see that the tape recorder is actually the speed is 2 times faster or 3 times faster, means that it's going to be compressed. The signal is going to be compressed. So in this case is that you're going to look at what are the scaling factor here. So we do not know what is scaling factor, so we just leave it blank first. So from here is that based on when you are going to use the scaling property, we are going to refer to the general value of period value, which is general period value is given by t equal to 1. Okay, based on this t equal to 1, then you determine what is the scaling factor. Okay, so from here is that, okay, we are going to refer to general t equal to 1. So if you have t equal to 1, then the signal looks like this. Okay, you have for t equal to 1 means that you have a period from minus tau over 2 to tau over 2. Okay, so if you rewrite again is that you have a rectangular t over 1, so you have a sin omega over 2. Okay, so let's jump to the next page here. Okay, next part here. So from here is that you have a equal to 1. So now is to find what are the scaling factor here. Okay, So find the scaling factor based on general t equal to 1, which is this part just now. Okay, based on this, we are going to look at what are the scaling factors. So look at this. So what is the scaling factor? You have the period is from minus t over 2 to t over 2, tau over 2. And for this signal is that you have minus t over 4 to t over 4. Means that the scaling factor is a equal to 2 because the signal is being compressed by 2 times. Okay, so you have a equal to 2. So when you have actually find out what is the scaling factor, then we can look at the appendix given. Okay, the Fourier transform table. Okay, you look at the property of Fourier transform table and find this. Okay, Fourier pair. So we have f in bracket at. So a is the scaling factor. Okay, so when you have this, you can get the Fourier transform of the equation ft is given by 1 over modular a f omega over a. So it means that directly just substitute the value of a here. Okay, so for the first step is that you have done the first step just now, which is this one. Okay, it's the same. So you get a is equal to 1, so substitute 1 here. So you have sin omega over 2, okay, which is from this part just now. Okay, and now we are going to write out with the scaling factor. So f a j omega. Okay, so you have a value, a is equal to 2. So a equal to 2 here, substitute inside this equation. Okay, this equation above, this one. So you have 1 over 2 sinc. Okay, means that what is the value for f omega over a just now? F omega is this signal. So f omega over a. So you have f omega is sinc, this one, substitute here, sinc omega over a. Okay, so you have omega here is the whole thing. This is omega from the initial value, so omega over 2 over a. So times over times, that's why here I multiply by 1 over 2. So you will get the final answer f a j omega equal to 1 over 2 sin omega over 4. So this is an example of using scaling property. Okay, of course, if you do not want to use the scaling property, you can always use the previous transformation. It means that you don't need to use scalar property but directly derive it from the Fourier transform equation. So now we're going to go to shifting property. Okay, so shifting property is when you have a signal. Normal signal is that you have the signal like this, it's being centered, okay, at 0 point. Right now, your signal right now your signal, you have the rectangular signal being shifted to the right side, which is delayed by 2, value 2. So similar to what you have did for the scaling property, first you need to find what is the a value. So a is amplitude, a is equal to 1. What is the t value? So t is 1, 2, 2. And what is t naught, which is the advanced or delayed? So you have the delay, okay, t equal to 2, okay, delayed. Okay, so for this case, we are going to do the example, okay, by not using any scaling property but directly using the Fourier transform pair. So we are going to look at the original equation here. Okay, so a rectangular t over t. So this is 2 is t. Okay, t, we have the period just now is 2, so t over 2. So we have a This one is t equal to 2a 2 sinc omega t over 2. Okay, so substitute that, you have the equation of 2a sinc omega. So if having look at this is that you can only use this a rectangle t over 2 when you have the rectangular centered at 0. Okay, at the original position, it's not being shifted anyway. So that's why first step is to find out what is the original signal when it's at the 0 point here, this point here, before it's being shifted. Okay, so first is to get that equation. Okay, next is that to use this Fourier transform property, which is for time shifting. Okay, so we have f t minus t naught. T naught is the shifting value. So means that for this case is that you will write f t minus 2. So that's why for this case is that you are going to write here xt is the original. Right now you are going to find it is what x equal x t minus t naught. This is t naught. Okay, so t naught is t minus 2. So you're going to find out what is xt minus 2. Okay, so if you look at the transformation pair, okay, to find out what is ft minus t naught is that you must first get the Fourier transformation for f omega. So which is what you did here. Okay, so you already got the Fourier transform for this signal, which is 2a sinc omega. Okay, so this one is f omega. Okay, dot e minus j omega t naught. So t naught, substitute it with the, oh sorry, not this one. Substitute it with the value t naught here. So t naught value is delayed by 2. Okay, so when you write the equation, substitute all the values. So you have 2, a is equal to 1, amplitude 1, sinc omega t, t is 2, 2 over 2, dot e minus j omega t naught. Okay, so when you simplify it, then you will get 2 sinc omega e minus j 2 omega.